This is AQA Statistics, Continuous Random Variable 6. This video is about hypothesis testing using the t-distribution. Let's start with a recap of the sampling distribution of the sample mean. Let's assume that x is a continuous random variable that is normally distributed with population parameters mu and sigma squared. Mu represents the population mean and sigma squared represents the population variance. If the population variance is known, then the sampling distribution of the sample mean is given by this distribution here. The sample mean is normally distributed with a mean equivalent to the population mean, but the variance of the sample mean is this term here. It is the population variance divided by the sample size. When conducting a hypothesis test for the population mean, this statistic here can be compared to the standard normal distribution. This is something that was in A-level maths. When conducting a hypothesis test for the population mean mu, if sigma squared is known, then this statistic is compared with the standard normal distribution. If sigma squared is not known, that is to say the population variance is not known, then instead of using the population variance, we substitute the sample variance, and instead of using the normal distribution, we use a new distribution known as the t-distribution. So this quantity here is calculated, and it is compared with the t-distribution, and the parameter here is the degrees of freedom. This is equivalent to the sample size minus 1. The t-distribution is a similar shape to the normal distribution, especially where the number of degrees of freedom is large. On the graph we have the standard normal curve, which is shown in blue, and we then have three t-curves. As the degrees of freedom is reduced, we see that the curve moves away from the standard normal curve. We can see that here, but very importantly, we can also see that here, and it is the difference in the tails that is so important. For a large value of the degrees of freedom, we could say if the degrees of freedom was large, then the t-curve will be very similar to the standard normal. But as the number of degrees of freedom reduces, we can see how the distributions do diverge, especially in the tails. Here is part of the table provided by AQA. The Greek letter nu is used to represent the number of degrees of freedom, and nu is equal to 1 less than the sample size. Each row of the table represents a different value for nu. The table is one-tailed, so the probabilities shown across the top of the table are equivalent to the shaded area in the graph above. Here's how we read the table, considering nu equal to 5 and the probability p equal to 0.95, we would read off a value for x of 2.015. If we were using the table for a hypothesis test for the population mean, and the alternative hypothesis was that mu is greater than mu naught, then x would represent the critical value, and values of t greater than x would represent the critical region. Supposing, however, we are doing the alternative hypothesis when mu is less than mu naught, the critical value x will be less than 0, and the critical region will be those values of t which are less than our critical value. By symmetry, we can see that the probability that x is less than minus 2.015 now is equal to 0.05. And this is the way we would have to use symmetry of the table if the alternative hypothesis is the less than case. Please pause the video to read the example. Here we are required to find the critical region for the test outlined here. We are given a normal population, but the variance is not given, so we must assume that it is not known. We should start by assuming a 5% level of significance for the test, as this is the default value. We can see that it's going to be a one-tailed test because we have the less than case. The sample size is 8, so the number of degrees of freedom is 7. Here is part of the AQA table. So looking at 7 and looking at 0.95, we see this value here, 1.895. But we are dealing with the less than case, so actually what we require is T7 at the 0.05 cumulative probability level, which will be equivalent to a value in the table of minus 1.895. The table, we derived the critical value for the less than case and the 5% level of significance of minus 1.895. This means that the critical region for this test quantity here is going to be less than minus 1.895. We have found the critical region for the hypothesis test, and we're now given sample statistics of sample mean of 9.05 and a sample standard deviation of 1.22. We're now required to complete the hypothesis test. What we need to do is to calculate this quantity here and find out whether it's in the critical region. When we calculate that value, we get the value minus 2.202. And if we now compare that to the critical region up above, we can see that this sampled value for t, minus 2.202, does lie in the critical region. This means that we can reject H0 and reach the conclusion that the population mean is less than 10. There is an optional method for conducting hypothesis tests, which is to calculate the exact p-value and compare it with the significance level. You would only be able to do this if you have a statistical calculator, and this is not a requirement of the further statistics course. What you can do is you can find the probability that the sample mean would take a value more extreme than the value that you have observed. In the calculator, we find the value of 0.0317, and we would compare this to 0.05. We see that as it is less than 0.05, there is evidence to reject the null hypothesis, and we carry on to reach the same conclusion as before. Please pause the video to read example 2. Calculate the sample mean and standard deviation using your calculator, and write down the null and alternative hypothesis. You should find that the sample mean x bar is 51.1 and the sample standard deviation is 0.476. In the calculator you may see Sx and sigma x. Now the one you want is Sx, you do not want sigma x. This is not the correct calculation for the sample standard deviation. The null hypothesis then, mu equal to 50.5, and the alternative hypothesis is the not equals to case, which means we will be dealing with a two-tailed test. You should notice though that the sampled value of the mean, the sample mean 51.1, is greater than the null hypothesis value. So therefore, the workings that we do are more similar to the greater than case. Let's carry on with the test now. We should assume the 5% level of significance because no other is given to us. This is a two-tailed test because we are dealing with the not equals to case, and the degrees of freedom is 4 because the sample size is 5. Here's part of the AQA table, and if we look along the row where nu equals to 4. Now, as this is a two-tailed test, we do require the value of p to be 0.975, and we're going to read this value off of the table here, 2.776, and this is the value that we require for as the critical value for the test, because the sample mean 51.1 is greater than the hypothesized value. So that means to say that we do need the upper tail as the critical value. The critical value we've just found from the table, and what we should now do is to use these values here to work out our level of sample t. If we substitute the numbers in, then our sampled value for t is 2.81. The sampled value for t is greater than the critical value, so this suggests that there is evidence to reject the null hypothesis and conclude that mu is not equal to 50.5. It would be reasonable to suggest that it appears that mu might be greater than 50.5. In example 1, we looked at an optional method for conducting the hypothesis test by calculating an exact p-value, and this is only available to students with statistical calculators, and it is not a requirement of the further statistics course. What you would do here is you would use the statistical calculator to find the probability that the sample mean would be greater than 51.1, so a more extreme value of the sample mean, and in the calculator we see that the value turns out to be 0.0242. Because it's a two-tailed test, that would be compared with 0.025, and there would be evidence to reject the null hypothesis. The calculators may show 0.0484 compared with 0.05. What happens there is that the probability gets doubled. That completes this video on hypothesis testing using the t-distribution. The next video is on finding confidence intervals using the t-distribution.